Good morning, good afternoon, everyone, and welcome to this week's edition of Canvas. Hope everybody's doing well. Today's speaker is Marnoosh Tahani, who is the Covington Fellow at the Dominion Radio Astrophysical Observatory in Penticton, part of the National Research Council of Canada. Marnoosh got her PhD in 2019 from the University of Calgary. So today she's going to be talking to us on the 3D morphology of magnetic fields associated with molecular clouds. It's all yours, Marnoosh.
Thank you. All right. Yeah, thank you very much, Dennis, for the introduction and for the opportunity. So today I'm going to talk about the 3D morphology of magnetic fields associated with molecular clouds. And I'd like to acknowledge my PhD advisors, Renee Bloom and Joanne Brown, and my collaborators, Ken Chen, Shuichiro Inotsuka, Yoni Kainulainen, Roland Coates, Ralph Podritz, Daniel Seifried, Juan Soler, and Jennifer West, who have contributed or are contributing to the different projects that I'll talk about today. So the talk today as a big picture focuses on magnetic fields in early phases of star formation, and more specifically it looks at magnetic field in filamentary molecular clouds, and it revolves around a new method that we propose and demonstrated based on Faraday rotation to detect the line of sight component of magnetic field in molecular clouds. So first, I'll give a brief introduction and I'll introduce the method, and then I'll talk about the results that we got from applying the method in different clouds and different regions. And then I'll talk about the interpretation of the results when we try to develop a full 3D picture of magnetic field in these clouds. So as we go along, this last box will be divided into three sub-branches that are the projects that we carried out to interpret our result. So we know that no astronauts have vacuumed the space between the stars, and we have the interstellar medium and interstellar clouds. And one type of interstellar clouds are molecular clouds that allow for formation of molecules inside themselves, and there are known to be the nurseries for star formation. So they allow for formation of stars within themselves. And various observations, including Herschel observations, showed that it's actually a dense filamentary structure, as you can see in the movie here, that are the nurseries for star formation and allow for formation of stars. So if we have a homogeneous cloud as simulated by Matthew Bate, as you saw in this movie, and if we perturb the cloud evolves and starts to form filamentary structure, and then these filamentary structure become gravitationally unstable and start to form stars within themselves. So the main idea is based on gravitational instability, but that's not the whole picture and the whole story of star formation. And there are other parameters here that are important in the star formation process, and one of them is magnetic fields. So the observations of magnetic field in the interstellar medium was started by Hiltner and Hall in an attempt to detect star-like polarization. So Hiltner, based on the observation, first hypothesized that these polarization that we're seeing is not actually due to the starlight, and it's actually due to the interstellar medium. And then very quickly, Hall confirmed Hiltner's observations and hypotheses and said that, yes, what we are seeing is actually due to the interstellar medium. And then again, very quickly, Davis and Greenstein explained this based on the alignment of the dust particles in the interstellar medium perpendicular to the galactic magnetic field. And then again, very quickly, Spitzer and Taki attributed this alignment to the ferromagnetic characteristics of dust grains. And we have come a long way since then, and we have various techniques to detect magnetic fields in the interstellar medium. And some of these include Faraday rotation, dust polarization, and Zeeman measurements. Faraday rotation has been widely used to detect the large-scale galactic magnetic field and magnetic field of ionized regions, and it provides the line of sight component of magnetic field. In the molecular clouds, both dust polarization and Zeeman measurements have been very successful in terms of mapping the magnetic fields in molecular clouds. Dust polarization is the same technique that we talked about, is due to the alignment of dust particles perpendicular to the magnetic field of the region. And there has been many observations, including Planck, Blaspol, Bistro, that map the plane of sky component of magnetic field in molecular clouds. So this image shows the drapery lines here show the magnetic field perpendicular to the, or in the plane of sky, in the Bella Sea region observed by Fistel et al. 2016. And I forgot to mention this cartoon, which is done by using Faraday observation by Van Eck et al., which provides a tomography of the galactic magnetic field. And then Zeeman measurements in molecular clouds provide the line of sight component of magnetic field, and to date, they are one of the most accurate ways to map the magnetic fields, especially in localized regions, and the line of sight. But because they're very time consuming, we proposed a new method based on Faraday rotation to detect the line of sight component of magnetic fields in molecular clouds. So what is Faraday rotation? When a linearly polarized light or electromagnetic wave passes through a region that is magnetized and has free electron, its plane of polarization rotates, and the amount of rotation is given by this formula, where lambda is the wavelength of the electromagnetic wave, Ne is the electron volume density in the region, B is the magnetic field in the region, and dl is the path length that the electromagnetic wave is going through. And the quantity in parentheses is known as rotation measure. So if we have information about rotation measure, we can get information about the magnetic field of the region. So for this method that I'll be talking about, we use extragalactic sources as point sources that provide the linearly polarized light for us. And the interstellar medium is the region where the Faraday rotation occurs. So now, to use Faraday rotation for molecular clouds, we have to answer two questions. We know that from the extragalactic sources to our receiver, the electromagnetic wave goes through the entire galaxy and entire interstellar medium. So the first question that we have to answer is that how do we decouple the contribution, the molecular cloud contribution, from the rest, which I call them as galactic contribution. And then after we've answered the first question, the second question that we have to answer is, remember in the formula we had the electron volume density and the path length. So how do we find the electron volume density and the path length to be able to find the magnetic field? So to answer the first question, we divided the integral into two parts, the contribution from the molecular cloud, and then the contribution from everything else along the line of sight, or the galactic contribution. The galactic contribution can be estimated by RM data points that have a position that fall near the molecular cloud, but are far enough away from it that are not affiliated with the molecular cloud. So I call these positions as off position, and the rotation measure is as rotation measure off. And then the on points or on positions or RM on are the points that fall on the molecular cloud or close to the molecular cloud. So now we can write RM on minus RM off gives us the rotation measure in the molecular cloud. So for this purpose, we use an already published rotation measure catalog by Taylor et al., which provides an almost full coverage of the sky with rotation measure point sources. So with this, we've answered the first question. And now, to answer the second question, we simplify the integral a bit further. We say, let's assume that the line of sight component of magnetic field in molecular cloud is roughly constant. So we take it out of the integral, and what we're left with is essentially the electron column density. And now, instead of finding the electron volume density and the path length, we only have to find the electron column density. So for that, we use extinction maps provided by Kainulainen and et al. 2009, and a chemical evolution code developed by René Bloom. So we have these three tools. Let's see how we can answer the second question. How can we find the electron column density? So using the extinction map, we make a map of the region. So here is the California region. The background shows extinction. Yeah, like the background shows the extinction, and this is in equatorial coordinate. So if I plot the rotation measure data, and it looks like something like this. I use blue to show positive rotation measure, and red to show negative rotation measure. So for simplicity, let's assume we have one rotation measure data. Let's just follow one rotation measure data point. So first we find the location of the data points on the map. So as the result, we have the extinction for that very point. And then using a conversion factor, we find the hydrogen column density in that region. At the same time, we simulate the chemistry of our cloud using our chemical evolution code. And so for different clouds, it's different based on the UV radiation, cosmic ionization, temperature, and the density of the cloud. And then as the result, we get abundances of elements versus extinction. And one of these elements is electron. So by having the extinction of that point, we have the electron abundance, and therefore we have, using the hydrogen column density, we have found the electron column density. So we've answered the second question. We can now go back to our formula and plot our line of sight magnetic field. So I use blue to show magnetic field toward us, and red to show magnetic field away from us. So just a little note that this is a simplified version of the method. Please refer to the paper and let me know if you have any questions. So to examine the method, we picked 4 regions of Orion-A, Orion-B, California, and Perseus. And what we found was that whenever we had nearby molecular Zeeman measurements available, our results were consistent or matched those Zeeman measurements within the uncertainty range. And so this map shows the California region again. The circles show the magnetic field. The blue show magnetic field toward us, red shows magnetic field away from us. So if we look a bit carefully, we see that at one side magnetic fields are pointing toward us, at the other side they're pointing away from us. So this magnetic field reversal across the cloud, we also see it in Orion-A region. And in Orion-A, this has been previously observed using Zeeman measurements. And it has been investigated in some theoretical studies. So in Orion-B, we did not have enough data points to make any conclusion regarding particular morphology. And then in Perseus cloud, even though we see some indication of reversal, we've been very cautious with our uncertainty analysis. And within the uncertainty range that we look at, we did not have enough data points to have a clear evidence of a reversal in this region yet. But we have VLA data for this region, and soon we'll be able to confirm or refute that. We also have data for more regions we will have soon, which are smaller scale. So we will be able to observe this reversal or non-reversal in more region. So 3 morphologies that have been proposed to explain these reversals are toroidal, helical, and a bow-shaped magnetic field morphology. In toroidal, magnetic fields form toroids around the filamentary structure. In helical, they form helices around the filamentary structure. And in bow-shaped morphology, regardless of how the filamentary structure is formed, typically the environment is known to be responsible to be interacting with the filamentary structure and bending the magnetic fields around the filamentary structure. In case of the Orion-A region, this responsible environment has been hypothesized to be the Orion-Eridanus superbubble. Okay, so far we've talked about the method and the results. What I'd like you to remember so far is that we used a new method, we proposed a new method, and we found reversal across filamentary structures. If there are no questions, I'll get to the interpretation of the results, which as a first step, we decided to combine our results with the techniques that provides the plane of sky component of magnetic field, and more specifically with the dust polarization data. And for this purpose, we picked Orion-A region. So yeah, for Orion-A, we had the line of sight magnetic field reversal that in the east side of the cloud, the magnetic field are pointing toward us, west side, they're pointing away from us. And we also have Planck observations by the Planck spacecraft that provides the plane of sky component of magnetic field. So
Hello?
Yeah.
Yeah, sorry to interrupt. I put some questions in chat, but no one seems to have seen them. Yeah, I wanted to ask a couple questions earlier.
Sure.
When determining the rotation measures, I mean, how do you deal with the n-pi radiant ambiguities?
So I used a rotation measure catalog that is already published for the result that I'm presenting here, which they use a technique based on depolarization to figure out the n-pi ambiguity. But typically when we have like a lot of bandwidth and we fit like in a classic approach, if we fit a linear fit to the data, when we plot polarization angle versus lambda squared, if we have n-pi for a certain data points, we will be able to do the unwrapping and find the rotation measure exactly. But for this work that I'm presenting, I did not do that myself. I used the catalog that is already published.
Okay. So in the chemical models you use to estimate electron abundance, there are many ambiguities, many parameters in chemical models. So there can be ambiguities in your results. So, I mean, how do you know that your electron abundances, those estimates are unique?
So we compared, that's a very good question. We compared the data, or like the electron abundances that we got with what we found from observations from different papers. I think one was Flower et al. I don't remember the year. And they seem to be in a good agreement. And then also like the final conclusion that like we seem to be consistent with the Sleeman measurements is also another confirmation for that. But in future upgrading of the method, we'll be also using like more sophisticated chemical evolution codes as well. But yeah, there is uncertainty in that, and we've been cautious in finding an uncertainty range for our data points.
Okay, thank you.
Yeah, no worries. Are there other questions? All right, so I'll yeah, I cannot see the chat window, so yeah, let me know if there are any questions. All right, so so we constructed models to represent the helical, toroidal, and bow-shaped morphologies. So I'm not showing the full equations or models here, but if you assume that the filamentary structure is just like a simple cylinder in this frame of reference that I'm showing here, with Z pointing toward us along the line of sight, X being radial in the plane of sky, radial away from the filament, and Y being along the main axis of the cylinder or filament. We constructed toroidal, helical, and bow-shaped morphology, and we have some assumptions for these to represent these three morphologies, because bow-shaped morphology typically needs environment, and then toroidal can also happen like in isolated filament or cylinders. So we have like physics assumptions for the equations as well, but you can see that in the toroidal, the magnetic fields are wrapping around the cylinder, and there's no Y components. In the helical, we do have a pitch angle, and then this component is not zero anymore. And then in the bow-shaped morphology, this is one of the simplest morphologies that we assume that represents a wrapping of magnetic field lines and is divergence-free. So we obtained synthetic observations from our models and compared them with observations. And because we are using two different methods, we also investigated the systematic biases between the two methods of Faraday rotation method that I explained, and then the Planck observation, and using a series of Monte Carlo analysis investigating systematic biases and chi-squared probability values. We concluded that toroidal is the least probable morphology to explain the magnetic field here in the Orion-A region. And then the bow-shaped morphology is the most probable case that can explain the reversal here. So we decided to expand this further to more regions, not only Orion-A, and looking into other models. And we decided to look at the models that explain the filamentary structure formation. So the model by Inutsuka et al. 2015 includes or considers a multi-compression scenario for the formation of filaments within dense clouds. And that typically includes a collision of dense H1 shells and dense clouds. So if for example, we have a dense cloud and H1 shell, and the cloud is moving with the velocity toward the cloud, we would expect bending of magnetic field around, they predict a bending of magnetic field around the formed filamentary structure within this cloud. So they further use ideal MHD. So these are MHD simulations by Inu et al. 2018, where they have a dense cloud. So it's 1,000 particle per centimeter cube, and an H1 shell, which is 100 particle per centimeter cube. And the cloud starts colliding with the velocity v in the H1 shell, and it starts forming dense filamentary structure within that region. And as the result, it bends the magnetic field in that environment, and the magnetic fields are also bent and wrapped around the filament that is formed, as you can see also in their cartoon in their paper. So if this bending is oriented from the Earth point of view, like what I'm showing here, we would be able to see or to observe a reversal across this filamentary structure. So here we would see magnetic field pointing away from us, and then we would be able to see magnetic field pointing toward us, as we see in the California region. So we decided to take a very simplified approach and look at the velocities of the clouds and see whether we can find any correlation across different clouds, and also between the clouds and the model that I'm presenting here. So if we have the velocities of the cloud and somehow we know some information about the initial magnetic field, can we predict the reversal, the orientation of reversal, and see whether it matches the orientation of reversal that that we observed or not? So we decided to take a simplified approach that if the velocities of current molecular cloud is conserved velocities from before collision, so if we know that velocity, like the cloud is moving away from us, we would expect to see a concave pattern, and if it's moving toward us, we would expect to see a convex pattern from the Earth point of view. And if the initial magnetic field of the region is pointing from the top of the page, pointing down, then we would expect to like the direction to be like somewhat conserved, and we would expect that the magnetic field at the top side would point away from us, at the bottom side in the concave pattern would point toward us, in the convex pattern would be the opposite. So with my co-op student, Wednesday Lupipchu at the Dominion Radio Astrophysical Observatory, who is doing her undergraduate studies at the University of Calgary, we decided to look at these three clouds, Orion-A, California, and Perseus, that in the case of these two clouds show a clear evidence of reversal, and in the case of Perseus show a very mild indication of a potential reversal. So for the initial magnetic field, we decided to look at the galactic magnetic field models, and we used the Hammurabi code, and more specifically, we used the Johnson-Ferrar 2012 galactic model. And for the velocities, we've used the molecular line velocities. And so far, we've found consistency between between all these clouds. So what we predict from the initial galactic magnetic field and the motion, the velocity of the cloud, they matches the orientation that the orientation of the reversal that we observed. And We have investigated this in a qualitative approach and also in a quantitative approach to where we came up with correlation coefficients to find the likelihood of the bowl-shaped morphology in these regions. And interestingly enough, even though Perseus didn't show a clear evidence of reversal initially, it seems to have the strongest likelihood to have a bowl-shaped morphology. All right, so any questions so far?
There's none in the chat.
All right. So
yes,
then,
sorry. Yeah, one question. I noticed a pattern, or maybe it's just my imagination. When the field is pointing towards us, it seems to be stronger than when it's pointing away from us, because the blue circles seem to be larger than the red circles. Is that just my imagination?
well, I don't have the numbers exactly, but yeah, no, that's correct. What I am seeing here, that's correct. In case of Orion-A, this study that we are conducting right now actually predicts a tilt of the Orion-A region, and then that would be explained, but also because like these clouds are not exactly oriented like perpendicular, like in the plane of sky, that would be a possible scenario. But also like regarding the strength, we have uncertainty range. So we have, like I have to do a clear analysis with this. Maybe Zeeman measurements would be a best way to compare the strength from in the two sides of these filamentary structure. Very good question.
It just seems systematic from what I see there. It looks systematic. It's not random. It's like their blues are almost always larger than the pinks.
Yeah, well, like from these we can't really say because I'm not showing the uncertainty range of these here as well, but yeah, I'll look into that. That's a very good question and point. Thank you. If there are there any questions? Okay, so we decided to explore these further and see how easy it is to form reversal in MHD simulations. Is it like very easy to form reversals in different orientation, or like more specifically, like how easy it is to form helical fields? So for that, we used magnetohydrodynamic or MHD simulations, and I used Flash, which is a high-performance, publicly available, multi-scale, multi-physics simulation code. And we simulated an isothermal cylinder showing our filaments. And we assumed a Plummer-like density profile for the filament, so the density drops as a function of radius away from the main axis of the filament. And we explored a wide range of parameter space, and we started with different initial orientation of magnetic fields. So for example, like perpendicular or parallel, and also we're exploring oblique magnetic fields currently. And remember that these simulations are 3D, so we can rotate and observe this scenario in a full 3D picture, so we're not limited by projection effects, and we can cut slices through and see this. So this movie here shows the density evolution as the time evolves in the filamentary structure. And so the filamentary structure starts evolving, and then it eventually forms cores and stars. So this simulation has perpendicular magnetic field to it, which are the initial magnetic field that we assumed in the region. And because we're interested to see the wrapping of the field lines or potential helical fields or bowl shape, one parameter that we introduced was rotation to the filament. And so to be able to, typically like in massive simulations, it gets a bit messy, but with these, it's clear. We can cut like sections through, everything is clean, it's an isolated filament. So if I cut sections in the Z direction, so along the line of sight in the filament, and go through the sections and look at the Z component of magnetic field. So blue shows magnetic field away from us, yellow shows magnetic field toward us. We see some reversal as we go. This is in the initial stages of the filament evolution, so it's in a fixed time. We see some reversal across the filament, but as we go further, the orientation of that reversal reverses, so it doesn't really add up to be like to show a reversal from the Earth point of view. And at the final stages, we see the same behavior. We see reversal in different sections of the filament. And it's somewhat uniform across the entire filament. But then again, the same thing, the orientation of reversal reverses. And if we look at as the X cut, so you're looking at the filament end on, in the initial stages, you have like a wrapping of magnetic field around this filament. And I should mention that this is a 1.6 parsec filament with initial magnetic field perpendicular to it and with 10 microgauss. So we do end up like seeing a wrapping of magnetic field around it. And this rotation frequency that we use is 7 times 10 to minus 14 hertz. That are the rotation frequency that we found from literature based on the velocity gradients across the filament. If we go to higher rotation, the twisting becomes a bit higher, but the general pattern is conserved. And then at the final stages where the gravity has taken over and the free fall time has passed, we do see a pinch of magnetic field or an hourglass morphology of magnetic field of the filament when you look at it as an end-on view. So far with the wide range of parameters, we have not seen any wrapping that produces a strong reversal from the Earth point of view. So with my summer student at National Taiwan University, Xin-Yu Chen, I'm sure I'm mispronouncing her name, who is co-supervised by Ken Chen at the National Taiwan University, we are introducing inhomogeneous environment to the filament. So it's still somewhat isolated and easy to look at the filament, but we are able to introduce them in homogeneous environment, for example, like different velocity patterns or shock or specific velocities from one direction of the cylinder to the other to see whether we can generate a strong reversal from the Earth point of view. And so far with the simulations that we've had, we've concluded that it's not really easy to generate helical fields on an isolated filament or a pre-existing filament, specifically via rotation. And for the bowl-shaped morphology, the environment is responsible, so this study will be actually looking at the bowl-shaped morphology. So I think I speeded up a bit. So as a summary, we proposed an demonstrated a new method based on Faraday rotation to detect the line of sight component of magnetic field in molecular clouds. And in Orion-A and in California, we saw a clear evidence of reversal across these regions. And in Perseus, we saw some mild indication of reversal. When we combined our results with the Planck observations, we saw that a bowl-shaped magnetic field morphology has a higher probability to be a responsible or like to be a possible magnetic field morphology in Orion-A. And then by using scenarios for molecular cloud formation or MHD simulation, they have so far strengthened the bowl-shaped conclusion for Orion-A and also for California and Perseus region. And then some final notes. I like to mention that magnetic field, understanding the 3D morphology of magnetic field in molecular clouds will enable us to understand not only the role of magnetic field in star formation, but we'll be able to distinguish between scenarios that propose molecular cloud and filamentary structure formation. And then we can also, by using MHD simulation, we can look at the cloud evolution and star formation and find the role of magnetic field, or take steps toward finding the role of magnetic field in star formation. And then Faraday rotation, Zeeman measurements, dust polarization together will help us more accurately find the 3D magnetic field morphologies in the clouds, in molecular clouds. And then we need to have continuous comparison between observations and simulation to help us better understand the role of magnetic field in star formation. Is it a friend of star formation, enemy, or both? And with that, I'm happy to take any questions.
Thank you, Mariusz.
Thank
Very
you.
interesting. Very interesting. Okay, let's start taking some questions. You can either raise your hand in the participant window, and Chris Matzner has a question already. Go ahead, Chris.
Hi, very interesting talk. Thank you, Mariusz. Question, so some of these regions have photoionization, and you would think that photoionization would produce an electron population that would dominate over what exists because of, weak photoionization or photoelectric effect going on inside of the molecular clouds themselves. So how do you control for the possibility of having a bit of photoionized gas dominate the rotation measure?
So if I understood the question, you're asking like how the free electrons that are produced as the result of photoionization control or contribute to the rotation measure here?
Yeah, I'm kind of assuming that that's not included in the chemical model in a detailed way. So is it something you you control for somehow?
Mm-hmm. So in the chemical code, as input parameters, we have UV ionization radiation from OB stars. So for example, for Orion-A, we have a higher UV ionization compared to California. And we also have cosmic ionization rate. So these are the two methods that are mainly contributing to the ionization in the chemical cloud, in the chemical code. and then yeah, like essentially by like decoupling the rotation measure of the cloud and finding the rotation measure of the cloud, and then like combining that with the chemical code, that helps us to find the line of sight magnetic field in these regions. But to answer your question, like in a brief sentence, the chemical code looks at the UV ionization rate and the cosmic ray ionization rate. Did I answer your question?
Yeah, you sort of. I'm just curious whether in the code itself you you find that the photoionized region, which would form self-consistently at the low column density portions of the cloud, whether that dominates the rotation measure, or whether it's free electrons embedded within the molecular material that dominate it.
Mm-hmm. So so when we start the code, like with the input parameters, we don't have anything further to produce or to contribute to ionization in the region.
Okay, maybe I can try to follow up with you later. I'm not
Oh,
quite
sure,
sure
yeah.
I understand.
Okay, yeah, sure. Yeah, sorry about that.
Okay, so if you have a question, you can either raise your hand in the participant panel, or if you want to, you can just type your question into the chat window.
Well, I have one question about it's about the electron density. Are there additional observations you can do to constrain that? It is an important question, and just to mention, the photoionization on the surface isn't necessarily dominate the ionization. It depends on the cosmic ray levels, which are dependent on the star formation rate. So you can have high ionization towards the center of the cloud.
Sorry, I'm trying to remember your question.
Are there observations to constrain the electron density?
Yeah. So the papers that I've looked at, to be honest, I've only looked at the final results that the observational paper that they quoted for the electron density in those regions, and I really don't know the methods that they're using. So I really don't know the answer to your question. Like whether we can constrain the electron densities that we can, so with the observations, I know that there are some available, but I don't know the methods to be able to see how they can well constrain and match our chemical result. And if you have any, so like I'm working on upgrading the method as we observe more regions. If you have thoughts, ideas that we can incorporate and embed in the code or like in the method, please let me know. It would be lovely to have you as a collaborator.
I'd like to make some comments. Can you hear me?
Yes, yeah.
Sorry, because it's my first time using Zoom. I'm Vic Kazauskas at Ottawa, and I'm a solar physicist. And there are fascinating parallels between what you are doing and how filaments form on the surface of the sun. But prior to that, I'd like to make sure that you're aware of the early work that Eugene Parker has done on how a collapsing gravitational cloud will entrap magnetic field with it and convert it into a toroidal work. I'm not sure if you're familiar with that early work of his or not. It's discussed in an annual reviews of astronomy and astrophysics around volume 10, somewhere there. It's a fascinating read. But to get back to the filament formation, what we find happening on the sun is that all the dense filaments, which are suspended in the low corona and have densities 2 orders of magnitude greater than the surrounding electron densities in the corona, occur over polarity inversion lines. So I'm quite excited to see their pictures showing these molecular clouds having opposite magnetic polarities on either side. And in the solar case, what my own research has shown, and other people's as well, is that this happens when you have two independent bipolar magnetic field systems moving together, and the joint, the filament will form where the two systems intersect. There's an extensive literature on this kind of formation. Much of it started by geophysicists of all people, names being Baum and Bratnall, who did a great deal of work along this line, and showing how you would get activity along this intersecting line. Now, my favorite version of how this happens with the sun is that you get reconnection between these two independent systems, and you generate enough Lorentz force that you actually lift up enough matter from the solar surface to be suspended in the very low corona. So yeah, I'd encourage you that has tackled some of these fascinating magnetic problems.
Thank you very much. Yeah, I wrote them down all. We had them like in my plasma physics course briefly, but I haven't had more in-depth studies. I'll make sure to review those. Thank you very much.
Okay, we still have time for any further questions. Okay, if not, I'd like to thank Mariusz again for a very interesting talk, very nicely presented, and look forward to seeing everybody perhaps at next week's Canvas meeting, Canvas talk, same time, same place. So have a good week, everyone.
Thank you very much.